Hello there. So again, we are here to discuss about mathematics behind machine learning. So in this video, we're going to see about linear transformation. So let's start the video. Have you ever looked at a matrix and thought it's just a bunch of numbers? Honestly, that's exactly how most of us first learn the linear algebra. Rows, columns, multiply them, take a determinants, find inverse, and repeat. But something always feels missing. Why is matrix multiplication defined this way? Why can someone matrices be inverted? And why do eigenvectors even exist? These ideas seem disconnected because we are only looking at the numbers, right? So let's talk about these missing pictures. Here's the secret. A matrix is not the main character. It's just a description. The real star of the linear algebra is something called a linear transformation, which we are going to see here. Think of a coffee machine. You don't care about every gear inside it. So you care about what happens when you put coffee beans inside the machine. Beans go in, coffee comes out, and the machine transforms the output. A matrix works in the same way. A vector goes in and the machine changes it, and it may stretch it, rotate it, reflect it, or shrink it, or combine several of these actions. That process is called a linear transformation. The matrix is simply the instruction manual for that transformation. Instead of focusing on the instruction sheet, we are going to understand the machine itself. So matrices are everywhere, but they are only the language, and linear transformations are the idea. Once you understand linear transformations, matrix multiplication won't feel like a formula. Inverse matrices won't seem mysterious, and vectors will finally have meaning. Everything starts fitting together. So, both before we study matrices, let's understand the transformations hiding behind them, because that's where the real story begins. We have learned the geometry of vector space, and we've been understanding the world where our data lives, and we have learned how to measure vectors, how to compare them, how to find distances, how to compute angles, and how to build coordinate system using bases. At this point, we completely understand the geometry of space. But machine learning isn't just about understanding space, it's about changing it. Here comes linear transformation. Let's understand it better with an example. A neural network doesn't simply receive an image and immediately says that's a cat. Instead, it transforms the data and again. Means it changes data from one feature space to another. At every layer, it creates a new representation of data. So each transformation helps reveal patterns that were hidden before and patterns which are hidden inside the data. Each layer takes one vector and produces another. This process is called transformation. Now imagine drawing a square grid on a rubber sheet. Now grab the sheet and stretch it, rotate it, shrink it, or shear it. The entire grid changes. But notice something interesting here. Straight lines remain straight, parallel lines remain parallel. The origin doesn't move. So, this is exactly what a linear transformation does. A linear transformation is a mapping between two vector spaces that preserve the algebraic structure, and functions between vector spaces are often called transformations. Let's talk about another example. Imagine we have two vectors x and y. We can combine them by scaling and adding them together. Now suppose we apply a transformation f to this combined vector. A transformation is called linear if this gives the same result. Then scaling and adding them afterward. It says transforming a combination of vectors is exactly the same as combining the transformed vectors. Because of this property, linear transformation preserves the basic rules of vector addition and scalar multiplication. That's why they are called linear. A linear transformation distributes over vector addition and scalar multiplication, just like multiplication distributes over addition. Let's understand with another example. The simplest linear transformation is called scaling. It is defined as f of x is equal to c into x, where c is a constant number. If c is equal to 2, the vector becomes twice as long. If c is equal to 0.5, then vector becomes half its original length. And if c is equal to in negative values, the vector flips to opposite direction. Now let's check if scaling is linear. First, combine two vectors ax plus by. Then scale the result using the distributive property. This is exactly the same as scaling each vector first, then combining them. Since scaling preserves vector addition and scalar multiplication, it satisfies the definition of a linear transformation. In fact, scaling is the simplest example of a linear transformation. Let's talk about the problem. Imagine I build a machine that transforms vectors. If you ask me, how does your machine transform every possible vector? Well, that's impossible to explain one by one. There are infinitely many vectors. So, how can we describe the entire transformation? Here's the secret. We don't need to know that what happens to every vector. We need only to know what happens to the basis vectors. Why? Because every vector is built from basis. So if we see the our example, the vector 3, 5 is simply 3 copies of the first basis vector and 5 copies of the second. Take another simple example. Transform the whole basis. Suppose our transformation moves the basis vectors like this. And that's all. So now we can transform every vector. Now take the vector 3, 5. Since it's made from 3 copies of first basis vector and 5 copies of second, after transformation it becomes 3 copies of the transformed first basis vector and 5 copies of the transformed second basis vector. And the final answer we'll get is 11, 18. Notice something amazing here. We never transformed 3, 5 directly. We only transformed the basis vectors. Now let's see where does the matrix come from. Now let's write the transformed basis vectors side by side. This is the matrix. The first column tells us where the first basis vector goes and the second column tells us where the second basis vector goes. That's it. A matrix is simply a compact way of storing a linear transformation. When we compute a into x, the computer isn't doing a random calculations. It's simply taking the coordinates of a vector 3 and 5 and combining the transformed basis vectors in the same proportions. That's exactly why matrix multiplication works. Example, in machine learning, when we input vector passing through a neural network layer, every dense layer in a neural network does exactly this. So it takes an input vector which is multiplies it by a matrix and produces a new representation. So every weight matrix inside a neural network is actually describing a linear transformation. A linear transformation is the action that changes vectors, and a matrix is just an instruction sheet that records where the basis vectors moves. Let's talk about invertibility of linear transformations. We have learned that a linear transformation changes vectors. Now let's ask an important question. Can we undo that transformation? If the answer is yes, the transformation is called invertible. For example, if a transformation doubles every vector, we can simply divide by 2 to get the original vector back. So this transformation is invertible. But if every vector is mapped to the 0 vector, then we can never know which vector was the original one. Information is lost. So this transformation is called invertible. Invertibility is extremely useful because it lets us solve systems of linear equation